Welcome everyone to the first lecture of the QSAR modeling course. In this lecture, we are going to discuss the main concept of the QSAR modeling subject. So QSAR stands for Quantitative Structure Activity Relationship. It is a computational drug design method, which means that it is done using computer software. And the main object of QSAR modeling is to be able to quantitatively predict the biological activity of structures, and it uses statistical methods to achieve so. So QSAR is mainly a ligand-based drug design method, which means that it requires a set of ligands with known activities to build a QSAR model. So as we can see here, for example, in this matrix, we are going to be dealing a lot with this type of tables or matrices where each row represents a chemical structure and each column represents a property of that structure. So in QSAR modeling, the structures are represented using molecular descriptors, which are simply numerical representation of these structures. So again, here we have this matrix where each row represents a structure and each column is a property of that structure. So we will talk about how to select descriptors later on and how they are used in QSAR modeling. And once we have computed the descriptors and we have the activities, so now we will have our structures represented numerically by the descriptors, and we have the activity in a numerical form. And hence we can use statistical analysis to derive the relationship between the descriptors and the activity. And this is the model that we get, or the equation is actually the QSAR model. Now let's look at what the term QSAR model actually means. So a QSAR model is a mathematical model in the form of equation. Now this simply means it's a mathematical equation which takes an input and gives you an output. So the equation is used to calculate the activity from the descriptors. So it's a function of the activity that's computed by the descriptors. So let's look at an example which demonstrates what this means. So this is an example of a QSAR model for computing the binding affinity to serum albumin. So this is a model that was derived using a set of ligands that have known activity towards the serum albumin. And the model that was obtained is the activity equals 0.75 multiplied by log P. Now log P is a molecular descriptor. It can be easily calculated using software. So when we have a new structure that we want to predict the activity for, we can simply compute the log P and get the estimated activity for the structure. Now as for this number, like the n equals 42 or the r squared, we will explain what this means in future lectures. So simply this means that there was 42 ligands that were used to derive this equation for the activity of serum albumin. Now this leads us to the QSAR model uses. So the first thing is the estimation of activity of new structures. So this is the main goal of almost all QSAR modeling approaches, is to be able to predict the activity of new structures with unknown activities. So for example, let's say we have this structure with unknown activity towards serum albumin. This is the equation which we just saw in the previous slide. Now to compute or to estimate the activity for this structure towards serum albumin, we simply need to use this equation. Now first we need to compute the log P, which is required by the equation, and computing log P for any structure is simple using many software. And once we have the log P value, we can plug it in the equation and then we can compute the activity. So now we get an estimated activity for these structures for binding to serum albumin. Now obviously how much you can trust this estimation or how accurate is this estimation, this depends on the model and how well it was validated, and we will discuss that in later sections. Now the other use of QSAR models is to understand the activity and the properties relationship. So a QSAR model can also help you to understand what properties or what descriptors are affecting the activity, and also how they are affecting the activity, like are they positively correlated or negatively correlated, and also how much variation of the activity they explain. So for example, in this equation we can tell that the log P is positively correlated with the activity, and also it is affecting the activity, which accounts for the hydrophobic characteristics of the structures. And also we can tell from the R squared that it is affecting the activity or explaining the variation in activity by 92%. Now how do we reach this conclusion, or how do we understand this? This is going to be explained in the regression analysis lecture, but this is just to give you an intuitive or an intuition about what are QSAR models and how they are used. Now, as for the applications of QSAR modeling in the drug discovery stages, now from the model uses which we just saw, obviously since they can be used to predict the activities of new structures, they can be used in virtual screening. So in the lead identification phase, we can use a QSAR model to predict activities of structures and get a new hits or new active structures. Also, they can be used in SAR analysis. So when we have different derivatives, we can use the model to predict their activities, also to prioritize which structures to synthesize and test first. Also, since they can be used to understand how the properties are affecting the activities, they can give insights or information about the properties that affect the activity, which can help in lead optimization in modifying these structures. So for example, in virtual screening, how QSAR is used is by first developing a QSAR model of on a certain target by using a set of ligands that are active against that target. So for example, we just saw a model for predicting the activities towards serum albumin. So when developing the model, we use set of ligands with active structures with the known activities, and once we obtain the model, we can then use it to predict activities of structures with unknown activities. And then, for example, we can screen a compounds database, and then we select the compounds that have the best predicted activities by the model and expect them to be actives. And finally, we will look at the advantages and disadvantages of the QSAR modeling approach in drug design. So the first advantage is that actually QSAR can give you a quantitative estimation of the activity, which is not present in other methods, like for example, pharmacophore modeling. They usually only classify the structure as active or inactive. Meanwhile, in QSAR, you can get a quantitative estimation of the activity, which is highly desirable. It's much more helpful. And then, given that the QSAR is a ligand-based method, it does not require a 3D crystal structure of the target. So in cases where the structure of the target is not present and we cannot use structure-based methods, we can use QSAR modeling. And also QSAR, there are many various methods because QSAR actually uses machine learning methods, which is a rapidly advancing field. You have a variety of methods to use. So sometimes if one method does not work well, you can try another statistical method to build your model and get better results. Now, as for the disadvantages of QSAR modeling, first thing is that the dataset properties for building a model can be difficult to meet. So the first thing is you need a dataset that have the biological activity known for the target, and you need to have a variation for the activity among other properties, which we will discuss later, but this is one of the main difficulties in QSAR modeling. Now, another thing is that the model you develop may not be usable on all the structures. Usually, it can be only applied on structures that are similar to the dataset. So, the model is not universal, it cannot be applied on any structure, but rather, usually, it has a specified applicability domain, meaning it can be only applied to certain structures that are similar to the training set structures. And finally, some methods that are not interpretable, meaning you cannot actually understand how the prediction is being made. So in the examples we saw, it was explainable. We could explain how the predictions are being made and how the properties are affecting the activity, but many methods do not provide that. They only provide predictions for the activity. So this concludes our first lecture on QSAR modeling. In the next lecture, we are going to look at the molecular descriptors and how they are used in QSAR modeling.